Okay, so let's talk about determining favorable sequences using the separating factor. Before that, remember that you need to go through some criterias after you validate the activity coefficients in your simulation. First, make sure that you identify the correct phase conditions for the separations that you're going to be proposing. Not all phase conditions in the feed can be suitable, and not all of the processes or units are available if you only have vapor, for example. Particularly for vapor-liquid mix, you can use the separation factor to narrow down your options. So it is important that you have a mixture of vapor and liquid. Depending on the composition, the separation factor may change. Here you have an equation, right, that relates the separating factor with the different K values. The K values can be obtained on HYSYS. Once you identify the K values, you calculate the separating factor or the relative volatility between the two adjacent pairs. And with that, you can go to this table on the right and determine which method may be suggested by this approach. Then you need to also couple this with a justification for the separation using heuristics and designer comments. Not all the pairs may be relevant for you. Maybe you want to do a cutoff where both reactants are leaving on the top, right, and they're send it back in using a recycle. So you really need to comment on the reasons why you're doing that separation, and if it's suitable, right, for the purpose of your design. You can always use this table to guide you and explore more in the literature to see how they simulate this and what options are good for your pair. Based on the total number of components, decide the number of possible sequences. There's a typo here, the number of possible sequences. This will help you to kind of like see what is the boundary, how many options do I have, how creative I can be in the way I organize my separations. Not all separations have to happen sequential, right, one after the other. You may have indirect separation, direct separation, or any combination of those as I explained before. Then the next step is to determine what is the favorable sequence, right? We already know that we have maybe 5 or 6 options that we can arrange our separation train, but now we need to use some heuristics, right, to help us guide our decision. So when the number of products in 3 or 4 components in a stream, you are trying to design and costing all the sequences, right, in a way that you find the most economical sequence at the end. So the most useful heuristics that you can use based on the concept of separating factor are: remove thermally unstable, corrosive, or chemically reactive components early in the sequence. Remember, these heuristics can help you to document and provide reasons on why you're doing a specific separation before the other. You can also, the second right heuristic is approximately equal easiness of separation. You have things with the same separating factor. Remove first components of highest molar flow or molar percentage in the feed. And the reason why we do this is that the total amount of moles, right, or molar flow impacts the subsequent size of the units that are going to be processing that total volume, and also affects the operating cost, right, because the energy transfer depends on the mass being processed. Also, remove final products one by one as distillates. That is the direct sequence. That is what we prefer, right, where the light key is the most volatile. There, when you do that sequence I explained before, you are using lower temperatures because the top or the light components have lower boiling points than the heavier ones, right, that have high boiling points, meaning that you need to add a lot of energy to it. Also because the efficiency of the separation is better. However, this depends, right? It's not that one heuristic is the winner. You need to combine them and make sure that it makes sense for your design. Also, if you add a separating agent, like a mass separating agent, remove it as soon as you use it. Don't send it again to the next column, because that will be increasing the total volume and diluting the next mixtures to separate. If the energy costs are high, sequence separation points that favor near equimolar amounts of distillate and bottom in each column. And we want to do this because we don't want to overwork the condenser and the reboiler, which are going to be related to the cost. Also, the right vapor liquid combination in the feed will avoid, right, that you have distributions of composition between the boilers and in the bottoms and the distillate. Sequence separation points to leave last those separations that give the highest purity products and minimize blending. And sequence separation points in the order of decreasing relative volatility so that the most difficult splits are made in the absence of other components. So if you notice, this is really connected to the number 3, right? That's pretty much what it's saying. It's kind of like telling you again how you can do actually the ones that are harder to separate. Typically the ones that are in the bottom or have very close boiling points, or you have an azeotrope. None of these heuristics require column design and costing at this point. This is actually one of the most creative parts of design within information that you have right now, coming up with the potential sequences, given the total number of sequences that you can propose. These heuristics often conflict with each other, so more than one sequence will be developed, and cost and other factors will need to be considered to develop the optimal final design. This is helping you to create your base case with the information that you have available right now. Remember that non-key components affect the separation of 2 key components. These non-key components can increase the reflux and boil-off requirements, which in turn increase column diameter and reboiler operating cost. This is really common when you have light gases like hydrogen, carbon dioxide. You try to separate those before you send them into a distillation column because they're gases, right? The boiling points are so different from the ones that you're trying to separate, right? The key components, that they tend to increase the condenser duty and the reboiler duty, depending on where they go. This and the number of trays are the major factors affecting the investment and operating cost of a distillation column. So you use this heuristic to guide you to create the best base case that you can create at this stage. So now what we're going to do is go over some examples so you can see how the separating factor can be used in your design.